The main goal of this video is to talk about applying template directives to types, something that I think we've seen coming. So we already know that we can create vectors, std vector objects of any element type. And we saw earlier this week that we could write all the machinery of a vector for ints, but we didn't quite understand yet how to add those angle brackets to allow our element type to be anything. But then in the previous video, we saw that we can use angle bracket notation and these placeholders to define templates. And it turns out we can use template directives not just on functions, but on types, and thereby create types that are generic, that can work with any element type in the case of collections. And we're going to use that, we're going to apply that in the next couple of weeks to be able to create things like a list of whatever, not just a list of ints, but a list of whatever element type you throw at it. And we could use that to construct vectors of any element type. In the meantime, for the sake of lodging that fact in here for this week's material, we're going to try a simpler example. I'm going to try and implement my own version of the std pair type. And I'm going to have my own function, make custom pair, that makes one of my custom pair objects. As we know, the std pair objects can be made with any two elements, so elements of any two types, and the make pair function has some magic to know how to return exactly what kind of pair object that I want. One of my ulterior motives in this video is to also talk about a different distinction, which is what is a struct and what is a class. So my basic example here is this type int pair, which is like an std pair object, but it only contains ints. And I'll scroll up to show the rest of the machinery. So I've implemented int pair as a struct because for now it's just a bucket of data. There's no behavior, no constructors, no private members, no member functions. And earlier in the course, we tended to use struct for this, by analogy to the old-fashioned C-style structs. We also know that if we have a struct with a bunch of members, which we'll hear in a minute, it turns out these members are public by default. You can use this unpacking or structured binding notation to take a structure or any other object like a pair that is a bunch of stuff and unpack it into individual variables, which is really convenient. And so I already have the machinery of a pair object ready. I've got my function to make the pair, I've got the pair type itself, I've used a struct for it because it's a very basic object, and I can even do the unpacking. So we'll just try running that to prove that point. So before I talk about templates, maybe we should answer the question, what is the difference between a class and a struct? So we've been using structs to represent basic buckets of data, and I abruptly switched to that word class once I started talking about things that had constructors and destructors and access control and member functions. So is that the difference? Is it that structs can only be just basic data and classes can have behavior? And the answer is not even close. It turns out in C++ they are basically identical with one difference. So first we can satisfy ourselves that if I made every member public, that in fact int pair could be a class. Interesting fact though. If I define a class and I don't include a public or private directive, everything in the class is automatically private. So that's why every class I've ever written, I've always started off by writing public. Because if you don't include the word public, everything in a class is automatically private. And we can see here, it's getting pretty upset. It's saying, sorry, I can't initialize the members because they're private, and then I can't use the members because they're private. And it actually turns out that a struct is identical to a class in every way except for that. So a struct can have constructors, a struct can have member functions. A struct can in fact have private members and public members and protected members. You can define subclasses of a struct. You can have, everything is the same except by default, if you don't put the word public or private, every member of a struct is public. So the only difference between class and struct is that by default, every member of a class is private unless otherwise stated, and by default, every member of a struct is public. Other than that, the two words are identical. So you could decide that every object you ever write will just be a struct that happens to have constructors, maybe it has subclasses, maybe it has access control and member functions, whatever. You could do that. And you could decide that every object you ever write is going to be a class where everything is public in cases where you want to use it like a struct. I instead will take a pretty nuanced opinion, which is that we tend to like the word struct to refer to basic data and the word class to refer to more complicated smart objects. I will use them that way. When I'm defining a type that is very basic and mostly just data, maybe it has constructors, maybe it doesn't, I will use struct. If, on the other hand, I want something encapsulated, especially something with private members, I will probably then use class. That is the difference. So anything I can do with a struct, I can do with a class, but if I don't put access control in either, then by default, a class has all of its members private, a struct has all of its members public. Now, let's work on the main problem for the video. So the main problem for the video is that, actually, I guess I should show this off. So if I define int pair as a class and I make every member public, the code will still compile. There it is, and we'll run it just to be absolutely sure. Good, okay, so we've proven that for completeness, we could in fact use struct and class almost interchangeably. I like the delineation of basic data should be a struct, more complicated things with smart behavior should be a class. Now, the main task for the video is I don't just want int pairs, I want this type called custom pair that are pairs of anything. Any two things can be put into a custom pair object. I could make a custom pair of int and int. I could make a custom pair of string and double. And just like the make pair function, I want my function make custom pair to handle whatever I throw at it, to make me a pair object of whatever types I give it. In fact, what I really want is the ability to eventually be able to write not just custom pair q, but auto q is just whatever the result from make custom pair is. So we'll just lodge that there and then come back to that at the end. We'll just comment it out. So in the meantime, I would like to make it so that my pair objects can be parameterized. So custom pair will have two parameter types that refer to the types of its two elements. And I want my make custom pair to use templates. Notice that I am not explicitly instantiating the template. I'm relying on the compiler using type deduction to figure out what the parameter types of make custom pair are going to be. Okay, so first, let's add a template directive to int pair. So I'll call it type name. I'll call it first type and type name second type. Recall that a template directive is sort of attached to whatever thing you stick it onto in the code, and it applies to that entire thing. When I attach the template directive to this struct declaration, everywhere inside of the curly brackets for the struct, I can then use the placeholders. So I can say that the element first is of type first type, the element second is of type second type. I can now attach a template directive to my make pair function. I guess I'll now rename the pair, not int pair, but custom pair. I'll rename make int pair to make custom pair. I will now say, I'm going to deliberately use different placeholders. I'll call them S and T. Okay, so make custom pair takes an argument of type S and an argument of type T, and it then constructs a custom pair object. And when we construct a custom pair object, we know that the custom pair object is parameterized. So it's a custom pair of element type. First type is S, second type is T, and we initialize it to be J and K, just like before. Actually, we'll call these first element and second element. J and K just have too much of an integer connotation. Okay, so there we go. First element and second element. So inside my make custom pair function, I create a custom pair object using the parameter types that I was given here. So whenever I invoke the template for custom pair, I have to say a custom pair of what? And so I give S as the type of the first element and T as the type of the second one. Then I call the constructor as usual because the type of result is just custom pair of S comma T. And then I return the result. And the return type is therefore custom pair of S and T. And because S and T are used as the argument types, the compiler should be able to deduce it. If I call make custom pair and I give it an int and a string, it should be able to figure out that I want S to be int and T to be string. It should be able to use deduction. That's the reason that the make pair function we've been using all semester didn't need angle brackets. The compiler, because I pass in arguments from which it can deduce the types, didn't need me to provide those type arguments explicitly. So we'll start by trying this. And I'll just compile and see if I missed anything. All right, looks like everything's good, so I'll try running it, and we'll just scroll down and take a look. So here, my variable p, just like in the original example with int pair, my variable p is a pair of int and int, 6 and 10. I print them out, I get 6 and 10. I unpack it. A and b will both now have type int, and their values will be 6 and 10. Then, and for certainty, I put them in variables to make it clear what their types are. I construct a pair where the first element's a string, the second element's a double. I get back a custom pair object of string and double. I print out q.first, it's the word raspberry. I print out q.second, it's the double value 10.6. I unpack it, so C would have the type string, D would have type double, and then I print them out to prove that I was unpacking them successfully. And then one final note, what I can do here is I can, because I know that the make custom pair function returns a value of a well-determined type, the compiler now knows the type of Q, there's no need to give it explicitly, and so I end up using notation very similar to what I would use for std pair earlier in the course, where I just call make pair, and the magic of templates takes care of everything else for me. Nowhere in line 42 do I need to name the types that I want my pair to contain. I just give it a string and a double, and templates do everything else for me.